Maybe could we just put a recording somewhere here? Is that
Oh, okay.
Okay. Yes, cannot share.
Sorry.
Duplicate screens is really like messing with your computer.
You can what?
That's good.
Yeah, this is one.
You have to just
I think I'm gonna put it here so you can record. Is that
We're
okay?
both-
Okay, we're both. Okay. Okay.
Okay. We're okay.
Okay. So hello everyone. So my name is Jiamian Hu. I'm an assistant professor in University of Wisconsin-Madison. So this work is done by my student, Shihao Zhuang. So I'm going to talk about the role of a foresight. Alex, I want to thank the organizer for this great opportunity to present this work, of course. And I'm going to talk about the role of polarization-photon coupling in ultrafast terahertz excitation of ferroelectrics. So why terahertz excitation of ferroelectrics? So in the previous talk, Han focused on the mid-IR region. So you have a 20 terahertz frequency, which cannot resonantly excite the soft mode phonon, which is the governing spontaneous polarization in perovskite ferroelectrics. So what if we use the terahertz pulse? So of course the source is less available than the mid-IR and other lasers. But the benefit of that is that we can resonantly excite the polarization. So it's more efficient and straightforward. It's simple as one term E dot P. So terahertz pulse is like electromagnetic wave. It contains both electric field and magnetic field components. We can directly change the direction of P and oscillate, make an oscillate. And this is like the incomplete list of the great works in the field. So we can use terahertz pulse to drive ultra-fast polarization switching, like the Andrew Rappe's group predict you can be using the series of a shape engineered terahertz pulse. You can reverse the polarization from up to down. And also Ignace, your group that does work in 2013 on ferroelectric nanowire using terahertz excitation as well. And this is an experimental study using the terahertz pulse to create new modes of collective excitation. Here's a arrow is atomic displacement, whereas the smaller arrow is the polarization. You can also, the Nielsen's group using the terahertz pulse to drive the transient phase transition in the quantum paraelectric STO by shifting the mode displacement. You can transiently drive, this is SHG singular. So when the electric field goes up, you can temporarily turn the material into a ferroelectric. And also, I think you will hear that from the next speaker, which you create new Rolin equilibrium phases by shining the short single cycle terahertz pulse in the relaxer ferroelectrics. So the question I want to ask is that it's based on basic Maxwell equation. Once your polarization start to oscillate at a picosecond time scale, you will have really strong radiation electric field. Like you show it here, shining the pulse, electric field make the polarization oscillate, you have radiation field going on. But what about the back action of that on the polarization dynamics? It's going to in turn affect the polarization dynamics. That is something we have experimentally, if you do it, the effect is there. But computationally, if we want to do the accurate prediction and modeling of these effects, this term needs to be considered, and that's the key point for my talk today. And specifically, you can see this governed by the partial P, partial T. If you change faster, you will have a larger radiation electric field, and this one will in turn influence the polarization dynamics. So key question is that, how does the field influence the frequency, oscillation frequency, which is also soft mode frequency, and the relaxation time of the polarization? So to do that, we consider a single domain BTO film, which is recently fabricated by my colleague Jiamian Onstep. They're doing this anisotropic implant stream plus interface engineering. I think Alexei, you did a PFM showing this is quite a single domain as well. We calculate the number of series, this is energy potential, and this is along the AB direction to have a double well, where on the CD the single well potential. So we first figure out what is the equilibrium state, then we do the excitation. And we use a single domain film to rule out the other at the simplest possible system to start with. Okay, so we solve this equation. This is since the P is proportional to the mode displacement, it's a mechanical oscillator equation. And then we solve the individual contribution of the total electric field here. And specifically, this EM is a radiation electric field. So you apply the electric field through terahertz pulse, you will have a radiation electric field. And we will show that the term is large and cannot be neglected. So we first do analytical solution. We have an analytical solution of that if you assume the oscillation is in the harmonic regime, which is the Hooke's law, force proportional to the displacement. And we assume this solution, and we also solve the Maxwell equation analytically for 1D system. And we can linearize this equation. We can get an analytical formula for the damping coefficient, which is inverse proportional to the relaxation time, and also the angular frequency of the phonon. So we can, then we do an analytical calculation, shows that, so this Y is the frequency, is the oscillation frequency of the PX, PY, and PZ. So soft mode, this is three-dimensional. They can have three. If you have the polarization, they can, depending on the landscape and energy, number of energy, they can have different oscillation frequency. And we show that we calculate as a function of the thickness of the film. In this case, the thin film is more interesting because we need a strand to make a single domain. We're assuming a single domain in our theory. If we look at the thin film regime here, the radiation electric field barely changes the oscillation frequency. However, it changed the relaxation time significantly. And so then we do things in parallel. We did a numerical model. This is this is our own in-house GPU-accelerated dynamic phase field model that couples the magnetization dynamics, elastodynamics, polarization dynamics, and electrodynamics. So the challenge of this kind of fully coupled multi-phase simulation is that, for example, if we want to simulate how do these vortices respond to the ultrafast Terahertz pulse, we need to use a really small cell to capture the unit cell-wise rotational polarization. So we need to use the 0.4 nanometers, which is also the limit of a mesoscale model about the unit cell size. And then the time step is determined by the quantity that propagates the fastest in this case, which is the EM wave. So if we do the calculation, it means that we need a time step of like 1 to -18 seconds per step to do the calculation accurately. And if we want to model the picosecond ultrafast dynamics, we need at least 1 million steps to model just for 1 picosecond. So it's really time consuming, but we solved that problem by GPU acceleration. Maybe there are some more intelligent algorithms, but we currently we're not yet. So we validate an individual solver. So with COMSOL, elastodynamics, the propagation of waves for micromagnetics, we compare that with the analytical calculation. We have a 3D finite difference time domain solver for the EM wave. This is the EM wave in a cavity. So you can potentially, we can do cavity enhanced night matter interaction in the ferro materials. And you can see our own codes have like 100 acceleration in this frequency. And all these modules are coupled. And for this problem, we only need the polarization dynamics and the electrodynamics. So here are the key results. So we show that this graph, the y-axis is the radiation electric field. The right y-axis is the applied terahertz pulse. You can see that this is 1.2 megavolt per meter. This is 0.2. So it's about 1/5 of it. It's pretty large. And it will cause significant change in the relaxation time if we consider the radiation electric field as you compare the oscillation of the polarization in these two curves. And this one, we're doing two things in parallel. This is fully numerical solution, and it agrees very well with our analytical model. So then, and in this case, we apply relatively small electric field to make sure the polarization is within a harmonic region so that we can make comparison to the analytical solution. And so you see that 1/5 of the applied pulse, and the oscillation frequency barely changes. And but this number also agrees very exactly well with our analytical solution. But relaxation time changes significantly in this case. Okay. We also studied the thickness dependence. So in this case, because our radiation electric field is the proportion to the thickness of the film, and we found that. So here's the damping, the frequency. The takeaway from here is that the oscillation frequency changes more significantly from here in the 50 nanometers in the thicker film. And if you compare here, again, here is with the radiation field. This is without the radiation field. The dynamics look very different. And also, according to basic theory, if you go thick enough, when the square root becomes negative, the polarization dynamics becoming critically damped and over damped. There's no oscillation in the thicker film. And this is also the same as the analytical prediction. Okay, so we're also studying the anharmonic region. So if you by applying larger electric field pulse, so kind of pushing all the way across to this region, and we found that a few things. If you compare this to the same thickness, the sample, well, virtual sample is the same, but this one has a larger electric field. And we found that the influence of the radiation electric field is more significant in the anharmonic regime. If you compare these two plots, the frequency here doesn't change at all. This frequency shifts more significantly. And this first is consistent with the existing experiment in the STO. And the second, the reason is that once you go to anharmonic regime, the slope is larger, so the effective field is larger, so the frequency is higher. And the simple message is that radiation electric field makes it harder to overcome the barrier. So if you want to use the terahertz pulse to drive the switching or to do things, this term is really important to consider. And we also did a control simulation that, because in the very beginning I said that the radiation electric field is only significant for the picosecond oscillation. So if you do the gigahertz electric field, it's not going to matter much. And so this result shows that we have a gigahertz pulse, electric field pulse, and it doesn't change much with the polarization. And the magnitude of the radiation field is also very weak. Okay. So to summarize this work, so we consider the influence of the polarization oscillation. It's kind of hard to read, but basically the radiation electric field is really important. And this is important because it allow us to accurately describe the experiments and to accurate prediction of this phenomenon. And we have our own GPU accelerated model that can do all these things. And particularly because we now kind of combine the ferroelectrics with photonics, we can directly solve the propagation of knot in a time domain in the ferroelectric materials. So this work has been published recently, and we are doing more work in this regard. For example, this is the preliminary data. This is vortices, polar vortices. We apply in terahertz pulse along the in-plane Y, in the diagonal direction. We show that it can achieve the ultra-fast reversal of the local polarization, this from down to up, and the vortex chirality in the same time. and everything happens only like 1.2 picoseconds. The entire thing only lasts 50 picoseconds. So, and also energy here is kind of higher than initial, so it's a metastable and non-equilibrium state. I have one slide which I'm really not sure I should show this. I asked ChatGPT yesterday about the topic, and the reason I want to say that right now I can confidently say that my knowledge can beat this a large language model, but I want to put a date here to see 1 year back if I can still do that, but I want to try to make some new innovation in this regard, okay? So then, and also yesterday, Google is kind of competing with Microsoft right now, launching this Bard AI in response to ChatGPT. I think we can, as time goes, this AI is going to help us to at least get a general overview of the knowledge in the field, but whether they say the correct or not, we need our own humans work together to push the field forward. Okay, with that, I'd like to thank you for your attention, and I'd like to take any questions you may have. Thank you.
So this presentation is open for questions, comments. Yes.
So I have a question about your time step. I think you will extend to the -80.
Yeah.
And I'm wondering why that would be. I didn't quite get that.
Okay.
Because it seems to be much smaller than I typically use in the section.
Right. Okay. Yeah, because in this case, we need to solve the propagation of EM wave. If you do the emission, it's emission in the vacuum. In the vacuum, you have a speed of light, and this when you solve this in a coupled manner, so time step is limited by that. This is for current condition FTDD model. So if we do not consider radiation field, it doesn't matter. But once you, essentially, we are looking at how does light propagate in a 0.4 nanometer cell. So this extreme combination makes this extremely time consuming. But I see this if you want to integrate with the photonics and do some different thing, that's kind of, maybe there's some no algorithm level innovation that can circumvent this problem.
So what did you talk with answers, but I need to switch over.
Sure, no problem. Yeah.
What did you talk about this ChatGPT?
What did I talk about the ChatGPT? Yeah, because I just saw the news from Google that launching the competition, and also I like to see what is the how do we, as time goes, how do we make use of that to facilitate our work? For example, you can.
Did you discuss your research?
No, I didn't. I'm trying to have a conversation with the chief, but not the real one. Yeah. 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 Yes.
So how do you get there? How do you make it material specific?
Oh, yeah. So we consider the BTO, so it's well studied, and we so in the paper I provided a list of table where the source. I think we cite the Anna Mozarovska's work. She did this the population dispersion, also the other works. I think, yeah, you can. I think you should be able to compute it from first principle. Maybe Karen can for this kind of damping or effective mass, that maybe that can be computed from first principle, if I understand correctly. I don't know. Sorry to put you there. Everything on first principle. Okay.
Okay.
Yeah. Yeah. Thank you very much.
Next computer is